Alright, so this is the next video on limits for Math 1560, Calculus 1 at the University of Lethbridge for fall 2017. In this video we're going to look at one more limit theorem, which is called the squeeze theorem. The squeeze theorem could be proved if we kind of had a careful definition of the limit, which we don't. But the squeeze theorem is pretty obvious once you kind of look at the picture, and so most people are generally happy to accept the squeeze theorem on face value. Now, here's another example of a limit that fails to exist, right? We've seen a few situations, different ways that a limit might not exist. We've seen that, if you have a graph that maybe does something like this, right, there's a break in the graph, then at that point where you have a break, the limit is not going to exist because as you come in from the left and as you come in from the right, the function can't agree on a y value that it's approaching. You might have something where you've got a vertical asymptote and the thing's going off to infinity. That's also another way that the limit could fail to exist. So there are a number of things that could go wrong. Here's one that fails in somehow an even stranger way, which is that, well, as x gets close to 0, 1 over x goes off to infinity. And what happens is that as you move in towards 0, the value of 1 over x hits a whole bunch of multiples of pi, if you like, right? And we know that, or even pi over 2, right? And we know that the sine function jumps back and forth between +1 and -1 as you go through multiples of pi over 2. And so if you take an interval containing 0, the function 1 over x is going to see infinitely many multiples of pi over 2. It's going to see a whole pile of them. And so this thing, it just, as you get in towards 0, this graph jumps back and forth infinitely often, and so that, you ask a computer to graph it, you just see this blur near 0. It can't even really plot it because it's going back and forth so fast that it just all kind of blends together. And no matter how much you zoom in on this thing, you're still going to see the same thing near the middle, right? So the limit can't possibly exist because the function is essentially seeing every single value between -1 and +1 in any interval that's close to 0. So there's no way you can have a limit here. Okay? Here are a couple of modifications, a couple of different things where you do have a limit. Now, in the first one, notice that we took our function with no limit, the one that we saw in the previous example, didn't have a limit, and we still have that sine 1 over x there, and you can still sort of see that it's bouncing back and forth and it's oscillating infinitely often as you get close to the origin. But as you get close to the origin, those oscillations get smaller. And so this time you can see that things are kind of being pinched or squeezed, if you like, towards 0, because the graph of sine of 1 over x, we know that the sine function, right, is always, for any angle theta, we know that sine theta is always between -1 and 1, and so if I multiply that thing by x, well, then it makes sense that the graph of sine 1 over x, if I multiply by x, that graph is going to be caught between the graphs of y equals x and the graph for y equals -x. So it's stuck in between, and because both of those graphs converge at the origin, the graph for x times sine 1 over x, that is kind of also forced to converge in towards the origin, and we do actually in this case get a limit of 0. Here's another one. This is actually quite an important limit that comes up quite a bit, sine x over x. So here you notice that this is another one of these 0 over 0 type limits, right? The top and the bottom are both going to 0 as x goes to 0. But this is a much trickier 0 over 0 limit because the techniques we used in the previous video don't apply. I can't factor out an x from the top in order to cancel it, right? I can't pull an x out of that sine function. X is stuck in there. And so I've got to come up with some other way of convincing us, well, looking at the graph, it sure looks like the limiting value for sine x over x as x goes to 0. It definitely looks like that limiting value should be 1. All right? How do we convince ourselves that that limiting value should be 1? Well, it turns out that both of these limits can be tackled. So this limit turns out to be 0. This limit turns out to be 1. And I can convince you of both of these if you agree that the following theorem is true, the squeeze theorem. Okay? So the squeeze theorem says you're dealing with three functions, f, g, and h. And you're in a situation where, and let me draw a picture, because once you have the picture, it's kind of clear what's going on. So you've got, let's say here's h of x, and here's f of x. So you've got two functions, right? And you've got two functions that come together at some point, right? That's this part here. There's some point where they have the same limit, and that means that the graphs must come together at that point. If they have the same limit, then the y values for those graphs, they're coming together. And you've got a third function, g of x, and g of x is stuck between the other two, right? So it might be going all over the place, but if it has to always be between the other two, it has no choice when it gets to this kind of pinching point, this squeeze point, right? It has to go in between there. And so if those two functions, the outside functions, f and h, if they have a limit of L, g is forced to have that exact same limit, right? So all three functions at that point must have the same limiting value. That's the squeeze theorem. I mean, when you draw a picture, it seems pretty obvious. A picture isn't always a proof, because you can come up with some weird and wild functions, things that you can't even necessarily graph, and so you can't rely 100% on the picture, but it gives you a pretty good idea of what's going on. Well, let's before I get to that, let's see how does that first limit work? How do I convince you that that first limit is true? Well, since I know that sine of 1 over x, regardless of the value of x, no matter how close it gets to 0, I know that sine of 1 over x has to be between minus 1 and plus 1. Well, that means if I take this inequality and I multiply the whole thing by x, I get to here. Now, if you're watching closely, you might notice that I've got to be a bit careful here. Okay, I really should consider two cases. I'm going to say x bigger than 0, y x bigger than 0, because if I do x less than 0, these inequalities are going to flip around on me and point the other way. But whichever way they point, the function I'm interested in, this one in the middle, it's still stuck in between x and minus x, and I certainly know that the limit as x approaches 0 of x and the limit as x approaches 0 of minus x, I know that both of those limits are 0, and because I know both those limits are 0, I know that the limit of the function in between must also be 0, and that's how I get that first limit. The other one, I'm not actually going to do it for you in this video. I'm going to set things up, and then we'll do the limit in the next video. But I'm drawing you a picture here. So why am I drawing you this picture? This picture is illustrating an angle. There's an angle, let's call that angle x. Here I've drawn it on the unit circle. Now, one of the things that we could do is we can think about, there's a few objects here that I might draw, okay? There's a little blue triangle that I could draw here, okay? And I know what the area of that little blue triangle is because I know what the length of the base is. Right triangle trig tells me that the adjacent side is cos x. The opposite side is sine x. And so the area of this little blue triangle, 1/2 base times height, cos x times sine x. I know that area. I don't actually need that area, but I do want to point out that that little triangle is similar to this big triangle, okay, because they both have all three angles the same. I know that the base of this big triangle is 1, and if you remember your similar triangles arguments, the ratios of sides have to be the same. So here I have this side y, and I don't know what that value is, but I know that the ratio of opposite over adjacent for the big triangle has to be the same as the ratio of opposite over adjacent for the little triangle. And sine over cos, well, we know what that is. It's tan. So the area, and I guess we'll maybe say that's the red triangle. Okay. So the area of the bigger red triangle is 1/2 times the length of the base, which is 1, times the height, which is 10x. One more triangle I want to throw at you. Right here, here, here. Okay? What's the area of that guy? The area of that triangle? Well, the height is still sine x, but the base now is 1. Okay, I stretched out the base while keeping the height the same. So it's 1/2 times 1 times sine x. Almost done. I've got one more thing. I need another color. Let's go with, I don't know, purple. Okay. The other thing I've got is I could do this pi piece. Okay. A sector of a circle. Now, I'm not going to go through the derivation of this, but if you've got a sector of a circle spanning an area x, well, one way to think of it, we know what the area of the whole circle is. It's pi r squared. R here is 1, so the area of the whole circle is pi, right? And that the whole circle corresponds to an angle of 2 pi. So if I only have a portion of that angle, if I kind of take the complete area, so it's basically my total area is pi, and then I take, well, what fraction of a whole angle do I have? X over 2 pi. So what do I get? I get x over 2. And now we can see that all of these triangles, they kind of fit one into the other, and in particular the ones I don't really care about the blue one, but what I do care about is that I have, and we're going to use, there's a reason for this, so bear with me, the green area, the 1/2 sine x is less than or equal to the purple area, which is 1/2 x, which is less than or equal to the red area, which is 1/2 tan x. Now, with a little bit of rearranging, and I'll leave this as an exercise for you guys to kind of play around with, multiply by everything by 2, you take some reciprocals, you divide by sine, there's a bit of work to do. You can work out that this is going to give you cos x less than or equal to sine x over x less than or equal to 1, and now you're set up to make a squeeze theorem argument about what happens to this guy in the middle as x goes to 0, and we will tackle that in the sequel.